The night sky over the northern hemisphere has been unusually generous this autumn, revealing its secrets to anyone willing to look up. In the hours before dawn, when the darkness is deepest and the Milky Way arches overhead like a river of ancient light, something new has entered our solar neighborhood. It's been there for weeks now, growing brighter with each passing night, a visitor from the space between stars that carries with it the cold vastness of interstellar distances. 3I/ATLAS, 3I-AT-LAS as astronomers call it, is currently about 140 million miles from Earth, roughly 1.5 times the distance between us and the Sun. That might seem impossibly far, and in human terms, it is. No spacecraft we've ever built could reach it in time. No telescope on Earth can resolve its actual surface into anything more than a point of light surrounded by a ghostly haze. Yet despite this enormous gulf, 3I/ATLAS is putting on a show that's visible even through backyard telescopes, growing bright enough that experienced observers with dark skies and patient eyes are starting to glimpse it with nothing but binoculars. The comet, and it is a comet despite its journey from beyond our sun's gravitational embrace, has been brightening faster than models predicted. In early September, it was a dim smudge requiring digital cameras and long exposures to capture. By mid-September, it had jumped nearly 2 magnitudes in brightness, a surge that sent ripples through the amateur astronomy community. Now, as October begins, it glows at magnitude 8, just below the threshold of naked eye visibility, but well within reach of anyone with basic equipment and a good star chart. But brightness alone doesn't make 3I/ATLAS remarkable. We see comets brighten all the time as they approach the sun, their ancient ices vaporizing in the solar heat, releasing gas and dust that catches sunlight and glows. What makes this object extraordinary is where it came from and where it's going. This is only the 3rd confirmed interstellar object ever detected passing through our solar system, a visitor that formed around another star in another stellar neighborhood billions of years ago. It spent eons drifting through the galaxy's darkness before chance and gravity brought it here, to this moment, to our sun. The previous interstellar visitor, ʻOumuamua, caused a sensation in 2017 precisely because we'd never seen anything like it before. That object was strange, elongated, tumbling, accelerating in ways that didn't quite match our predictions. It sparked thousands of scientific papers and, inevitably, speculation about artificial origins that persisted long after more mundane explanations emerged. But ʻOumuamua was also disappointing in its brevity. By the time astronomers realized what they were looking at, it was already leaving, receding back into interstellar space. We had only weeks to study it, and it never came close enough to reveal much detail. 3I/ATLAS is different. This visitor is approaching us, not leaving. It will make its closest pass by Mars on October 3rd, swinging within about 4 million miles of the red planet, close enough that NASA's Mars orbiters might catch a glimpse if they orient their instruments correctly. Then, in late October, it will reach perihelion, its closest approach to the Sun, diving inside the orbit of Venus before being flung back out toward the stars from which it came. Along the way, on October 21st, it will pass almost directly between Earth and the Sun from our perspective, an alignment called conjunction that will make observation temporarily impossible, but also creates a natural crescendo to its performance. What astronomers are watching now in these early October nights is a comet in transformation. Every day brings subtle changes. The coma, the fuzzy envelope of gas and dust surrounding the nucleus, grows larger and more complex. Jets of material erupt from the surface as different ices reach their vaporization temperatures. The tail, which should stream behind the comet like cosmic hair blown by the solar wind, has begun to show something peculiar. Several observers have reported seeing what appears to be a second tail, one that points in the wrong direction, not away from the Sun as basic physics demands, but toward it. The images are subtle, easy to dismiss as artifacts or processing errors, but they're appearing in photographs from different observers, using different equipment under different skies. Something about 3I/ATLAS's geometry, or our viewing angle, or the interplay of dust and light, is creating an illusion that's both beautiful and disorienting. The phenomenon has a name among comet specialists, an anti-tail, though that term is almost a misnomer because there's nothing anti about it in the sense of opposing forces. It's a trick of perspective, a reminder that we're viewing a three-dimensional object travelling through three-dimensional space from a single vantage point that's itself in motion. The dust particles that form a comet's tail don't simply stream away. They fall into their own orbits around the sun, creating a curved sheet of debris that can, from certain angles, appear to point in impossible directions. But here's where the story deepens. Anti-tails are typically seen in comets that have made many passes through the inner solar system, comets whose orbits and dust patterns are well established. They're rare even then, requiring a precise alignment between the comet, the sun, and Earth. For an interstellar visitor making its first and only journey through our neighborhood, for a comet whose composition and behavior are still largely unknown, to display this phenomenon seems almost impossibly coincidental. Unless, of course, something else is happening. Unless 3I/ATLAS is releasing dust in an unusual pattern, or rotating in an unexpected way, or carrying some compositional quirk inherited from its formation around a star unlike our own. These are the possibilities that have observers refreshing telescope images every night, comparing notes on forums and messaging apps, watching for changes that might reveal something fundamental about where this visitor came from and what it's made of. The October 3rd Mars flyby looms just days away now. After that, 3I/ATLAS will be closer, brighter, and potentially more active as the sun's heat intensifies. The anti-tail phenomenon, if it's real and not just a temporary alignment, should become more pronounced, or perhaps reveal itself as something else entirely. But for now, in these early October nights, there's only the watching and the waiting. There's only the image of a fuzzy star with a tail that seems to defy the rules, a visitor from darkness that's holding up a mirror to our understanding of how the universe works. What is 3I/ATLAS really showing us in these tail-twisted nights before its closest approach? The first person to notice the anomaly was an amateur astronomer in rural Spain, imaging the comet on the night of September 27th. She almost dismissed it, a faint spike extending from the coma in the wrong direction, barely visible in her stacked exposures. It could have been a satellite trail that the stacking software failed to remove, or a cosmic ray hit, or any of a dozen technical artifacts that plague astrophotography. But something made her look closer, adjusting the image stretch, enhancing the contrast. The spike persisted. It was real. She posted the image to a comet observation forum with a simple question: is anyone else seeing this? Within hours, observers from Chile, Australia, and California confirmed it. Each image showed the same feature: a narrow, faint projection extending from the head of the comet, not along the expected dust tail, which streamed away from the sun, but pointing almost directly back toward it. The geometry was wrong, or rather, it was unexpected enough to demand an explanation. The physics of comet tails is, in principle, straightforward. Sunlight and the solar wind, that constant stream of charged particles flowing outward from our star, push gas and dust away from a comet's nucleus. The gas, ionized by solar radiation, forms a bluish ion tail that points almost exactly opposite the sun, like a windsock in a cosmic breeze. The dust, heavier and less affected by electromagnetic forces, forms a yellowish tail that curves gently as the particles fall into their own orbits. Both tails always point generally away from the sun. They have to. That's what radiation pressure and solar wind do. Except when they don't. Or rather, except when they appear not to. The anti-tail phenomenon has been known since the 1800s, when observers first sketched comets showing this impossible spike. It took decades to understand what they were seeing. The key insight is that a comet's dust tail isn't a simple stream. It's a sheet, a flat disk of particles spread along the comet's orbital plane. Most of the time, we view this sheet from an angle, and we see only the illuminated edge. the familiar curved tail. But when Earth crosses the plane of the comet's orbit, our perspective changes. Suddenly, we're looking edge-on at the dust sheet and particles on the far side of the comet's orbit. Particles that are technically behind the nucleus from the Sun's perspective can appear to project forward because of our viewing geometry. It's like watching a frisbee edge-on. From certain angles, parts of the disk appear to stick out in front, even though nothing is actually moving forward. The antitail is a perspective effect, a reminder that the cosmos doesn't arrange itself for our viewing convenience. But here's what made the 3I/ATLAS antitail strange: the timing and the sharpness. Earth wouldn't cross the comet's orbital plane until mid-October, according to the preliminary orbit calculations. Yet the antitail was already visible in late September, fainter than it would become, but unmistakably present. And unlike the soft, diffuse antitails seen in well-studied periodic comets, this one appeared almost needle-like, a narrow spike that suggested either an unusually concentrated dust distribution or something about the particle sizes and ejection velocities that didn't match typical comets. Speculation began to swirl through the astronomy community. Was 3I/ATLAS releasing dust in jets rather than the more uniform fountain typically seen? Was the nucleus rotating rapidly, creating a spiral pattern in the dust that happened to align with our viewing angle? Or, and this was the possibility that kept observers checking their equipment, could there be outgassing happening from the side of the nucleus facing the Sun, creating a forward-directed plume that only looked like an antitail? That last possibility, if true, would be significant. Comets occasionally show forward-facing jets when gas erupts from sun-facing vents, but these are typically short-lived and associated with sudden outbursts. A sustained forward plume from an interstellar comet could reveal something about its composition, perhaps ices that sublimate at different temperatures than the water and carbon dioxide that dominate solar system comets. Ices formed in the colder environment of a different stellar system, or modified by eons of exposure to cosmic rays during the journey between stars. The images kept coming. An observer in New Mexico captured the antitail extending nearly a quarter of the width of the main coma. A professional observatory in Hawaii, alerted to the phenomenon, turned one of their smaller research telescopes toward 3I/ATLAS and confirmed the structure in multiple filters, showing that the antitail appeared in both visible light and near-infrared, suggesting it was composed of dust particles reflecting sunlight rather than glowing gas. And each night, as October approached, the antitail grew more pronounced. Not brighter exactly, but more defined, as if the comet was sharpening its geometry for our benefit. By October 1st, even modest backyard telescopes could capture it with long enough exposures. The comet was becoming a textbook example of a phenomenon that shouldn't be this easy to observe in an interstellar visitor. The question shifted from "is this real?" to "what does this mean?" Why would a comet making its first passage through our inner solar system, a comet that had never felt the heat of our Sun before, produce such a classic and pronounced antitail effect? The dust creating this illusion had to be spread in a specific geometric pattern, particles following precise orbits that happened to align with our viewing angle at just the right time. Coincidence was possible. The universe is large, and improbable alignments happen constantly somewhere, but there was also the nagging possibility that 3I/ATLAS was telling us something, that its interstellar origin had given it properties, spin, composition, outgassing patterns, that made this phenomenon not a coincidence, but a natural consequence of where it came from and what it was made of. What secret was hiding in plain sight, written in dust across the darkness between a comet and the Sun? The story of 3I/ATLAS began not in October, but in April, when the ATLAS survey telescopes in Hawaii, automated systems designed to scan the sky for asteroids that might threaten Earth, caught a faint smudge moving against the background stars. At first, it was unremarkable, magnitude 19, barely brighter than thousands of other distant objects that pass through the survey's nightly hall. The automated systems flagged it, calculated a preliminary orbit, and sent it to the Minor Planet Center for cataloging. But the orbit was wrong. Not wrong in the sense of being inaccurate. The mathematics checked out. Wrong in the sense of being impossible for a solar system object. The eccentricity was greater than 1, meaning the trajectory was not a closed ellipse, but an open hyperbola. The object wasn't orbiting the Sun, it was passing through, following a path that would carry it back out to interstellar space once the Sun's gravity released it. Within a week, observatories around the world confirmed the orbit and the object's interstellar origin. Spectroscopic observations showed absorption lines consistent with water ice, carbon monoxide, and cyanogen, materials common in solar system comets. Radio telescopes detected no emissions suggesting unusual composition. Infrared observations estimated the nucleus at somewhere between 0.5 mile and 2 miles across, comparable in size to many short-period comets. 3I/ATLAS appeared to be, in most respects, ordinary. Just a comet that happened to come from somewhere else. Through the summer months, it brightened slowly as it fell sunward, following predictions with comforting accuracy. Professional observatories checked in periodically, adding data points to the light curve, the graph of brightness over time that tells the story of a comet's activity. Amateur observers began tracking it as it climbed from magnitude 15 to 13 to 11, each step representing a roughly 2.5-fold increase in brightness. Then, in mid-September, something changed. The light curve, which had been following a smooth power law increase, brightness rising as a predictable function of decreasing distance from the Sun, suddenly jumped. Over just 3 nights, 3I/ATLAS brightened by nearly 2 magnitudes, the equivalent of a 6-fold increase in light output. It was as if someone had flipped a switch inside the nucleus, activating new vents or exposing fresh ice to solar heating. Outbursts aren't unusual in comets. The surface of a comet nucleus is a chaotic landscape of ice cliffs, dust mantles, and subsurface voids. As the Sun heats different regions, pressure can build beneath the surface until something gives way. A chunk of crust collapses, a void ruptures, a jet of gas explosively vents. The comet brightens dramatically for days or weeks, then settles back to a new baseline. But 3I/ATLAS's outburst had unusual characteristics. First, it didn't fully fade. After the initial surge, the comet stabilized at a brightness level significantly higher than pre-outburst models predicted. Something had fundamentally changed in how much material the nucleus was releasing. Second, the outburst coincided with the appearance of the anti-tail structure. The timing suggested the two phenomena might be related. Perhaps the outburst had ejected a cloud of large dust particles into a particular geometry, creating the conditions for the anti-tail illusion. By the last week of September, 3I/ATLAS was magnitude 8 and accelerating toward its October 3rd encounter with Mars. The distance between the comet and the red planet was shrinking by more than 1 million miles per day. NASA's Mars Reconnaissance Orbiter, equipped with a high-resolution camera designed to photograph the Martian surface, received uploaded instructions to attempt a long-distance observation during closest approach. The chances of capturing useful data were slim. 4 million miles is enormous by human standards, and the comet would appear as little more than a smudge even to the orbiter's sensitive instruments. But the opportunity was too rare to ignore. If the observation succeeded, it would mark the first time a spacecraft had photographed an interstellar object from close range. Even a blurry image could reveal details about the comet's structure, the dust distribution, the behavior of this visitor from beyond. Ground-based observers worldwide prepared for the flyby with their own instruments. Radio telescopes would listen for any unusual emissions. Spectroscopes would analyze the light for clues about composition. High-speed cameras would watch for changes in brightness that might indicate rotational variation or new outbursts. The comet would be closest to Mars at approximately 1400 hours UTC on October 3rd, early morning in the Americas, afternoon in Europe, evening in Asia. The whole world would have a window to watch, weather and daylight permitting. The anti-tail, meanwhile, continued to sharpen. By October 2nd, it extended nearly half the width of the Sun as seen from Earth, about 15 arc-minutes or 1/4 of a degree. The main dust tail had also grown, now stretching more than 2 moon-widths across the pre-dawn sky, a ghostly banner visible in binoculars from dark sights. The coma itself had expanded to nearly 5 arc-minutes, large enough that higher-power telescopes could begin to resolve structure within it. Jets or fans of brighter material, a denser core, asymmetries that suggested the nucleus was rotating with one hemisphere more active than the other. All of this activity, the outburst, the anti-tail, the expanding coma, was happening as 3 I/ATLAS plunged deeper into the Sun's influence. The solar heating was increasing exponentially with decreasing distance, warming ices that had been frozen for billions of years, forcing this interstellar wanderer to transform itself from a dark, dormant rock into an active, brilliant comet right before our instruments. The October 3rd flyby would be a milestone, but it was only the beginning. After Mars, the comet would continue sunward, growing brighter and more active until it reached perihelion in late October, at a distance closer than Venus. The real show, the peak brightness, the maximum tail development, the potential for dramatic outbursts, was still ahead. But the question that kept astronomers returning to their telescopes night after night wasn't about what would happen at perihelion. It was about what was happening now in these early October nights, as 3 I/ATLAS displayed behavior that seemed too perfect, too textbook for a first-time visitor. Could a comet from another star system really mimic so precisely the behavior of comets that had orbited our Sun for millions of years? The global astronomy community has a rhythm to it, a pulse that follows the turning of the Earth. As sunset sweeps westward across time zones, observatories wake, first Australia and Japan, then India and the Middle East, then Europe, then the Americas. By the night of October 2nd, that pulse was synchronized, focused on a single fuzzy star climbing through the pre-dawn constellations. In Arizona, an amateur astronomer with a 14-inch telescope and a cooled CCD camera set up in his driveway, laptop glowing in the darkness as he polar aligned his mount with the meticulous care of someone who knows that precision now means better tracking later. He'd been imaging 3 I/ATLAS for 2 weeks, posting his results to an online forum where other observers could compare notes and techniques. Tonight, he was hunting for detail in the coma, hoping to catch those jets and fans that hinted at a rotating, actively venting nucleus. In the Atacama Desert of Chile, one of the world's premier dark sky sites, a professional research team had booked time on a 1-meter telescope specifically to study the anti-tail. Their plan, multi-filter photometry and polarimetry, measurements that would reveal the size and composition of the dust particles creating the forward-pointing spike. Dust in space doesn't scatter light randomly. The physics of how photons bounce off particles depends on the particle's size, shape, and material. By measuring how polarized the reflected light was, they could constrain whether the anti-tail consisted of fluffy aggregates or compact grains, pristine ice or radiation-processed organics. In Western Australia, a team of citizen scientists had coordinated a simultaneous imaging campaign, planning to capture 3 I/ATLAS from multiple locations over a 3-hour window. If the comet's brightness varied on short timescales, a sign of rapid rotation or pulsed outgassing, the synchronized observations might catch it. They were using modest equipment, nothing like the professional instruments in Chile, but they had enthusiasm and numbers and a shared determination to contribute something meaningful to the understanding of this visitor. And aboard the Mars Reconnaissance Orbiter, 140 million miles from Earth and 4 million miles from 3 I/ATLAS, a sequence of commands executed with mechanical precision. The spacecraft, designed to photograph the Martian surface in exquisite detail, rotated slightly, pointing its high-resolution camera away from the planet and toward a patch of star-filled space where orbital mechanics said a comet should be. The exposure would be long by spacecraft standards, several seconds, enough for trailing if the pointing wasn't perfect, but the target was faint and distant, and sensitivity mattered more than sharpness. The image, when it came, would take hours to download through the deep space network, the data trickling back to Earth at kilobits per second across the vast gulf. No one expected a miracle, but even a detection, even a fuzzy blob confirming the comet's position, would be worth it. Back on Earth, as the Arizona observer began his imaging sequence, 3I/ATLAS revealed itself in his first 10-minute exposure. The coma appeared as a soft greenish glow, that distinctive color produced by diatomic carbon, a molecule common in comets that fluoresces in sunlight. The greenish tint is a signature of comets throughout the solar system, a reassuring sign that whatever star 3I/ATLAS formed around, the chemistry there wasn't too different from what happens around our sun, but embedded in that green glow were structures, a bright, almost stellar core, the unresolved nucleus surrounded by its densest cloud of gas and dust. Radiating from the core 3 or 4 distinct jets, brighter streamers that suggested localized venting from specific areas on the nucleus. The jets weren't symmetric, they fanned out more strongly to one side, indicating that the nucleus's rotation was carrying active vents into and out of sunlight as the comet tumbled through space. And there, unmistakable even in this single exposure, was the anti-tail, a narrow spike extending back toward the eastern sky, toward the direction of the sun's position below the horizon. The observer enhanced the image, stretching the contrast until the faint structure became obvious. The anti-tail wasn't smooth, it showed a granular texture as if composed of discrete clumps of dust rather than a uniform stream. That texture might be real, or it might be noise in the image, the random uncertainty that plagues all deep sky photography. Only more data, more images could tell. He uploaded the image to the forum with a timestamp and his location. Within minutes, responses came from Europe, where dawn was beginning to interfere with observations, but where earlier images from the night showed similar structure. The Chilean team reported their first results. Preliminary polarimetry suggested the anti-tail dust consisted of particles larger than typical comet dust, perhaps 1/10 of a millimeter across, instead of the few micron sizes that dominate normal tails. Larger particles meant different dynamics, different response to solar radiation pressure, potentially different ejection mechanisms from the nucleus. The Australian coordinated campaign collected its data as local midnight approached, multiple observers sampling the comet's brightness at 15-minute intervals. The preliminary analysis, conducted in real time via group chat, showed no obvious variation. If 3I/ATLAS's nucleus was rotating, it wasn't producing brightness changes large enough to detect with their equipment. That suggested either a slow rotation or a nucleus shape that was relatively symmetric, or active regions distributed around the surface rather than concentrated in one spot. All night, the data accumulated, spectra showing emission lines of carbon, cyanogen, hydroxyl radicals, the usual suspects in comet chemistry, photometry tracking the overall brightness, confirming that the comet remained steady at magnitude 8, still elevated from its pre-outburst predictions but not undergoing new dramatic changes, astrometry precisely measuring the position against background stars, data that would feed into refined orbit calculations. And on Mars, as October 3rd's dawn broke over the spacecraft's ground track, the Mars Reconnaissance Orbiter completed its observation and turned back to its primary mission, imaging the rust-colored surface scrolling below. The comet data was in memory, waiting for downlink, a small file among thousands of images of craters and canyons and ancient riverbeds. What the spacecraft had seen, whether it had captured anything at all, would remain unknown for hours yet. But on Earth, under stars that would soon fade into morning twilight, observers saved their final images, packed up equipment, uploaded data to shared repositories. The October 3rd encounter was complete. 3I/ATLAS had passed Mars, missing by 4 million miles, a near miss by cosmic standards, but an enormous gulf in human terms. The comet continued sunward, indifferent to the attention, following the gravity-curved path that would carry it toward perihelion and the October 21st conjunction beyond. Behind it, in its wake, a growing stream of data and images and measurements that would take months to fully analyze. But already, in the first light discussions and preliminary reports, a pattern was emerging. 3I/ATLAS was behaving like a comet that knew what it was doing, a visitor that seemed to have read the manual on how solar system comets should act. The outburst timing, the anti-tail geometry, the chemical composition, the brightness evolution, all of it fit within the range of known comet behavior, even as the particulars suggested this object wasn't quite typical. It was similar enough to reassure, different enough to intrigue, and with 2 weeks remaining until the October 21st conjunction, when the comet would pass almost directly between Earth and the Sun before vanishing into the solar glare, every night of observation mattered. What was this interstellar visitor teaching us about the universe beyond our own star's influence? The Mars Reconnaissance Orbiter image arrived in pieces, downloaded over several hours through the Deep Space Network's antenna in Canberra, Australia. When the file was complete and opened by the mission team, there was a collective moment of held breath, then quiet satisfaction. The comet was there, a faint, slightly elongated smudge against the star field, exactly where the orbit predictions said it would be. Not a detailed image, not a revelation, but a confirmation. A spacecraft had photographed an interstellar object. History, in a small way, had been made. But the real story that emerged on October 3rd wasn't from space. It was from a comparison of images taken from Earth over the previous week. A careful analysis that finally explained the anti-tail in a way that was both beautifully simple and slightly disappointing. The Chilean research team, working with their polarimetry data and consulting with orbital dynamics specialists, had modeled 3I/ATLAS's dust distribution in 3 dimensions. They input the comet's trajectory, Earth's position, the timing of the September outburst, and the observed properties of the dust. The simulation showed that the outburst had indeed ejected a cloud of larger-than-average particles, and those particles had spread into a disk along the comet's orbital plane, just as theory predicted. What made the anti-tail so pronounced, the model revealed, was a combination of factors. First, the September outburst happened at a point in the comet's trajectory where the orbital geometry was nearly ideal for creating an anti-tail effect from Earth's perspective. The particles ejected during the outburst had spread both ahead of and behind the nucleus in its orbit, creating a thick concentration of dust in just the right position. Second, Earth's motion was carrying us toward the plane of the comet's orbit slightly earlier than initial calculations had suggested, because the orbit itself was being refined as more observations came in. We'd entered the viewing geometry for the anti-tail effect sooner than expected, which explained why it appeared in late September rather than mid-October. And third, this was the detail that made some observers smile with the recognition of a cosmic joke. The dust particles were indeed larger than typical, about 1/10 of a millimeter, which meant they scattered light efficiently and appeared brighter than the fine dust in the main tail. The anti-tail looked sharp and well-defined, not because of anything exotic about 3I/ATLAS's composition or behavior, but because the dust particles were just the right size to be easily visible. It was, in other words, a textbook anti-tail produced by textbook physics. The comet from beyond our solar system was following the same rules as comets that had never left our sun's neighborhood. When the explanation circulated through the astronomy community, reactions were mixed. Some felt a twinge of deflation. There would be no revolutionary discovery here, no exotic interstellar phenomenon requiring new physics. The anti-tail was beautiful, yes, and wonderfully clear, but it was understood. Others felt vindicated, even relieved. The universe was consistent. The physics of dust and light worked the same way around other stars. 3I/ATLAS, for all its exotic origin, was just a comet. But there was also a more subtle realization spreading among those who'd been following the observations most closely. If 3I/ATLAS was so similar to solar system comets, what did that say about comet formation in general? Comets are thought to be pristine remnants from the formation of planetary systems, icy leftovers that preserve the conditions and materials present when stars are born. If a comet from another stellar system had the same ices, the same dust, the same behavior as our own comets, then perhaps the chemistry of planet formation was more universal than we dared assume. Or perhaps, and this was speculation, the kind of hypothesis that would require many more interstellar visitors to test, 3I/ATLAS had formed in a stellar environment remarkably similar to our own. Not all stars are alike. Some are hotter, some cooler, some richer in heavy elements, some starved. The comet's composition suggested it came from a system with temperatures and chemistry similar to the early solar nebula, the cloud that collapsed to form our Sun and planets 4.6 billion years ago. That narrowed the possibilities, pointed towards Sun-like stars as 3I/ATLAS's origin. The comparison with ʻOumuamua was inevitable. That first confirmed interstellar visitor had been strange precisely because it didn't behave like a comet. It showed no detectable coma, no tail, no outgassing, yet it accelerated as if pushed by venting gas. Its shape appeared highly elongated, unlike any asteroid or comet nucleus observed up close. It tumbled chaotically through space, its light curve varying in ways that suggested a bizarre geometry. ʻOumuamua had challenged expectations. 3I/ATLAS was confirming them. Some researchers argued this made 3I/ATLAS more valuable scientifically, not less. The strange objects tell us the universe has variety, but the ordinary objects tell us what's common, what's typical, what we should expect from the galaxy at large. If most interstellar comets behave like 3I/ATLAS, active, icy, chemically familiar, then we can start to build a statistical understanding of planet formation around other stars. We can say with growing confidence that solar systems elsewhere probably look a lot like ours. But a quieter, more philosophical interpretation also circulated in blog posts and late-night observatory conversations. Maybe the lesson of 3I/ATLAS was humility. We'd been ready for it to be weird, armed with instruments and questions designed to probe the exotic. Instead, it arrived and simply was, a comet being a comet, following the laws that govern such things, indifferent to our hopes for revelation. In a universe that often resists easy understanding that remains stubbornly strange at every scale we examine, here was something we could grasp. Here was something that made sense. The October 21st conjunction was still ahead, the moment when 3I/ATLAS would pass between Earth and the Sun from our perspective, vanishing into the solar glare. After conjunction, it would re-emerge in the evening sky, rapidly fading as it receded from both the Sun and Earth, heading back toward the interstellar medium. Observations would continue until the comet dimmed below the threshold of even the largest telescopes, probably sometime in December. But the story's climax, in a way, had already passed. The anti-tail mystery was solved. The Mars flyby was complete. The comet's nature, icy, active, ordinary, in all the extraordinary ways comets are ordinary, was established. What remained was documentation, the careful gathering of data that would contribute to scientific papers and catalogues and our slowly growing census of interstellar objects. The tone had shifted from wonder to acceptance, from the thrill of the unknown to the satisfaction of understanding. 3I/ATLAS had given us a gift, though perhaps not the one we'd expected. It had shown us that we weren't entirely lost, that our knowledge could extend beyond the sun's influence, that a visitor from the stars could arrive and speak a language we already knew how to interpret. Was that enough to find familiarity in the cosmos instead of strangeness? In the days following the Mars flyby and the explanation of the anti-tail, observatories faced a quiet decision. Keep watching 3I/ATLAS intensively. Dedicate precious telescope time and human attention to an object whose major mysteries had been resolved. Or shift resources to other projects, other questions, other parts of the sky that might yield more novel discoveries. It's a choice that underlies all of astronomy, a field perpetually constrained by the limitations of equipment, time, and funding. Every hour spent on one object is an hour not spent on another. Every photon collected from a well-understood comet is a photon not collected from a distant quasar or an exoplanet transit or a supernova in a neighboring galaxy. Science is as much about prioritization as it is about curiosity. For some observers, the decision was easy. They would continue watching 3I/ATLAS because it was there, because the October 21st conjunction promised a beautiful geometric alignment, because the ongoing data would contribute to the complete light curve and help refine models of interstellar comet behavior. The project had momentum. They would see it through. For others, particularly professionals with oversubscribed instruments and competitive proposal processes, the calculus was more complex. Yes, 3I/ATLAS was intrinsically interesting. Yes, every measurement contributed to science. But was it the best use of a large telescope on a clear night? Would the data collected change our understanding in significant ways? Or would it be incremental, confirmatory, the kind of careful work that's necessary but not transformative? There's no right answer to questions like these. Science advances both through leaps of unexpected discovery and through the patient accumulation of detail. The breakthrough that reshapes a field often comes from the unexpected, the anomaly that doesn't fit. But the understanding that makes breakthroughs possible comes from the grinding work of characterization, of measuring and cataloging and building statistical samples large enough to reveal patterns. 3I/ATLAS sat at an interesting boundary. 3I/ATLAS sat at an interesting boundary. It wasn't going to revolutionize our understanding of comets. The basic physics was sound, the behavior well within expected parameters. But it was only the second interstellar comet ever studied in detail, the second data point in what would eventually need to be a large sample before astronomers could confidently say anything about the population of icy bodies drifting between the stars. Two comets don't make a pattern. Two comets barely make a comparison. ʻOumuamua had been strange. 3I/ATLAS was ordinary, and from those two examples alone, no one could reasonably conclude anything except that interstellar objects have variety. Were most of them like 3I/ATLAS? Or was ʻOumuamua more typical, and this comet the outlier? Would the next visitor be stranger still, or would it slot neatly into the growing taxonomy? These questions would take decades to answer. Interstellar objects are rare. Current estimates suggest maybe one passes through the inner solar system per year, but most go undetected, too faint or too far from Earth when they make their closest approach. Building a sample of even a dozen well-studied interstellar visitors might take the rest of the century, requiring not just luck, but also next-generation survey telescopes designed to scan the entire sky every few nights, catching these transients before they slip away. So every measurement of 3I/ATLAS mattered, even if each individual data point seemed incremental. The detailed light curve would help astronomers recognize similar objects in the future. The spectroscopic data would provide a compositional benchmark. The dust properties would inform models of how comets release material as they approach stars. And the successful coordination between professional observatories, amateur astronomers, and even spacecraft, the Mars Reconnaissance Orbiter observation, however limited, demonstrated that humanity could respond quickly and effectively when something interesting appeared in the sky. That coordination was itself a kind of achievement. Astronomy has always been a global enterprise, but it hasn't always been a collaborative one. Telescope time is competitive, credit for discoveries can be contentious, and the pressures of publish or perish academia sometimes create incentives to hoard data rather than share it. Yet 3I/ATLAS had inspired a different approach. Images and measurements were being posted publicly within hours of collection. International teams were forming spontaneously, pooling data from different instruments to achieve results no single observatory could manage alone. Amateur astronomers were contributing observations that complemented professional work, filling gaps in coverage and providing continuous monitoring that scheduled telescope time couldn't match. In a small way, 3I/ATLAS was reminding the astronomical community of something easy to forget. They were all looking at the same sky, asking versions of the same questions, driven by the same fundamental curiosity about the universe and our place in it. But beyond the scientific and sociological dimensions, there was something else happening in these mid-October nights, something harder to quantify but no less real. For the thousands of people worldwide who had turned their telescopes toward 3I/ATLAS, who had stayed up late processing images or discussing observations in online forums, the comet had become personal in a way that's specific to amateur astronomy. When you spend hours coaxing photons from a faint smudge near the horizon, when you watch that smudge gradually resolve into structure through your laptop screen, when you see the anti-tail appear in your own images, not in some professional publication, but in data you collected yourself, the object stops being an abstraction. It becomes real in a visceral way, a thing you've touched with your own instruments, a visitor you've witnessed with your own efforts. This is the gift that amateur astronomy offers to those who practice it, the direct, unmediated experience of the cosmos. Not the universe as described in textbooks or presented in processed images from space telescopes, but the actual sky, right now, tonight, available to anyone with the curiosity and patience to look. And what 3I/ATLAS was offering, to both professional and amateur observers alike, was an opportunity to exercise that curiosity and patience in service of something genuinely rare. Yes, the comet was behaving ordinarily. Yes, the major mysteries had been explained, but ordinariness doesn't mean unimportant, and understanding doesn't erase wonder. The choice then wasn't really about whether to keep observing. Observers would observe because that's what they do, because the comet was there and the telescopes were there, and the convergence of those facts creates its own imperative. The choice was about attitude, about how to frame the remaining 2 weeks before conjunction. This could be seen as documentation, the dutiful completion of a project whose excitement had already peaked, or it could be seen as witness, the privilege of watching an ancient traveller complete its brief visit before returning to the dark. Both perspectives were valid, both were true. Science often operates in this dual mode, simultaneously rigorous and romantic, collecting data while also simply paying attention to the universe in all its casual magnificence. The October 21st conjunction would come regardless of how anyone felt about it. The geometry was set, the orbits determined. 3I/ATLAS would slide between Earth and the Sun, vanish into the glare, and re-emerge on the other side to begin its long fade back into interstellar space. Humanity would watch as much of this as circumstances allowed, then return to scanning the sky for the next visitor, whenever and whatever it might be. In the meantime, there were still nights to observe, images to collect, light curves to extend. There was still a comet in the sky that had travelled for eons to be here, now, in this narrow window of visibility. And there were still people willing to stay up late, to fight cold and fatigue and technical difficulties for the chance to see it clearly. That willingness, that commitment to witness, might be the most human part of the entire endeavour. We are a species that looks up, that wonders, that builds instruments to extend our senses across vast distances. We are creatures who care about visitors from the dark, who invest meaning in dust and ice that couldn't possibly care about us in return. Is that impulse, to watch, to study, to simply be present for these cosmic events, a strength or a peculiarity of our nature? The sky above the northern hemisphere shifts as October deepens. The pre-dawn hour when 3I/ATLAS first rose has been sliding earlier each night, the comet climbing higher before the first hint of twilight washes it out. By October 15th, it's visible in truly dark skies, the Milky Way still arching overhead when the comet appears above the eastern horizon. The geometry is becoming more challenging for observers, the angle to the sun tightening as conjunction approaches, but the comet itself continues to brighten. Magnitude 7 now, just barely naked eye visible from exceptional dark sights, though most observers still need binoculars or telescopes. The anti-tail remains, though it's starting to fade as Earth's viewing angle shifts. The main dust tail has grown even more impressive, stretching nearly 3 moon widths across the sky in long exposure images, a ghostly arc that captures the imagination of everyone who manages to photograph it. The coma is huge now, larger than the full moon as seen from Earth, though so diffuse that it appears as a soft glow rather than a sharp disk. Professional observations have tapered off as predicted. A few dedicated programs continue, collecting spectroscopic data that will eventually be published in papers analyzing the comet's composition and comparing it to solar system analogues. But most major telescopes have moved on to other targets, other questions. The October 21st conjunction will make observation impossible anyway, so there's little point in intensive coverage during these final days. Amateur astronomers, freed from the constraints of proposal committees and scheduled telescope time, have kept watching. Their images continue to flow into online repositories, a crowd-sourced monitoring campaign that captures 3I/ATLAS almost every clear night from somewhere on Earth. The quality varies. Some observers have professional-grade equipment, others are working with modest telescopes and entry-level cameras. But the collective coverage is extraordinary. When historians someday look back at humanity's observation of this interstellar visitor, they'll find not just a handful of archival images from research observatories, but thousands of pictures from hundreds of individuals who simply wanted to see it for themselves. On October 18th, 3 days before conjunction, an observer in Japan captures something unusual, a brief brightening, a surge that lasts less than an hour before fading back to normal levels. It's subtle, easily within the noise for most equipment, but several observers in the same time zone confirm it independently, a minor outburst perhaps, or a rotation bringing an active region into optimal viewing. The event is noted, discussed, added to the observational record. It doesn't change the overall narrative of 3I/ATLAS's behavior, but it's a reminder that even a well-understood comet remains dynamic, capable of small surprises. The October 21st conjunction arrives with mixed weather across the northern hemisphere. Cloud cover obscures the comet for many observers during what should be their final viewing opportunity before the sun's glare intervenes. Others have clear skies and make the most of it, capturing final images that show 3I/ATLAS now deep in twilight, the sky already brightening with approaching dawn, the comet a faint smudge barely distinguishable from the background glow. By noon, UTC on October 21st, the geometry becomes impossible. From Earth's perspective, 3I/ATLAS is within a few degrees of the Sun, lost in the overwhelming glare. Solar observatories with specialized coronagraphs, instruments designed to block the Sun's direct light, scan for the comet, but it's too faint and too far from the Sun's disk to appear in their fields of view. For several days, 3I/ATLAS is invisible to humanity, an object that still exists, still travels, still vents gas and dust into space, but does so unseen. It re-emerges in the evening sky on October 25th, visible to Southern Hemisphere observers as a faint object low in the western twilight after sunset. The geometry has flipped. What was a morning comet is now an evening one, and what was best viewed from northern latitudes now favours the south. Observers in Chile, Australia, South Africa and New Zealand take up the watch, continuing the observational record as 3I/ATLAS begins its long fade. The comet is past perihelion now, receding from both the Sun and Earth, and the brightness that peaked near magnitude 6.5 just before conjunction is already dimming. By the end of October, it's back to magnitude 8. By mid-November, magnitude 10. The tail, so impressive in early October, contracts as the production of gas and dust decreases with distance from the Sun. The anti-tail is gone entirely, a month-long phenomenon that existed only during that perfect alignment of geometry and timing. Professional publications begin to appear, preliminary reports, abstracts submitted to conferences, early analyses of the spectroscopic data. The papers describe a comet with water ice, carbon monoxide, carbon dioxide, and organic compounds, a composition indistinguishable from long-period comets native to our solar system. The dust properties match predictions. The brightness evolution, accounting for the September outburst, follows expected patterns. 3I/ATLAS is, as suspected, an ordinary comet that happened to come from elsewhere. But ordinary is a relative term. For the researchers who spent months planning observations and analyzing data, for the amateur astronomers who captured it in their own images, for the spacecraft that photographed it from Mars orbit, 3I/ATLAS was anything but ordinary. It was a visitor, a wanderer, a messenger from the galaxy at large. It was confirmation that our understanding of comets extends beyond our own solar system, and simultaneously a reminder that we've observed only a tiny fraction of the icy bodies drifting through interstellar space. By December, 3I/ATLAS fades below magnitude 15, visible only to large professional telescopes. The last confirmed observation comes from an observatory in Hawaii, the same survey system that discovered it 8 months earlier, on December 23rd. After that, the comet is too faint, too distant, receding along its hyperbolic trajectory back toward the interstellar medium. It will take years for 3I/ATLAS to fully escape the Sun's gravitational influence, decades before it's truly in interstellar space again. But from humanity's perspective, it's already gone, already transitioned from an object of active study to a memory, a data set, a collection of images and measurements that will be analyzed and reanalyzed as techniques improve and questions evolve. Somewhere in that data, in the thousands of images and hundreds of spectra and countless measurements of position and brightness, lies everything 3I/ATLAS had to teach us. The lessons might not all be obvious yet. Science often works that way. Understanding emerges slowly from data, patterns revealing themselves only when enough examples accumulate, when context develops, when the right question is finally asked. The next interstellar visitor might arrive next year, or might not come for a decade. It might be another ordinary comet like 3I/ATLAS, or something strange like ʻOumuamua, or something entirely unexpected that forces astronomers to expand their categories and rethink their assumptions. The galaxy is large, and the types of objects it produces are surely more varied than our small sample suggests. But whatever comes next, whenever it comes, humanity will be watching. The survey telescopes will keep scanning, the global community of observers will keep coordinating, the instruments will keep improving. We are, as a species, committed to paying attention to the cosmos, to bearing witness to these visitors from the dark, to collecting every photon we can capture before they slip away. In the end, 3I/ATLAS asked us the question that every transient phenomenon asks: will you watch? Will you make the effort, invest the time, turn your instruments and attention towards something fleeting? And by watching, will you allow yourself to be changed, even slightly, by the knowledge that the universe is larger and more intricate than any one lifetime can fully explore? The answers came in telescope time and image uploads, in late nights and early mornings, in the coordination of observers across continents and the careful analysis of data that will contribute to our slowly growing understanding. They came in the form of action, of showing up, of doing the work, because the universe presented an opportunity and we chose to meet it. As 3I/ATLAS recedes into the dark from which it came, as the excitement of early October fades into the routine of archival analysis and paper writing, a question lingers in the minds of those who watched most closely. Not a question about the comet itself, that's been answered as much as it can be with current data, but a question about us, about why we care, about what draws us to look up at visitors from the void and invest them with meaning they don't inherently possess. Maybe the answer is simpler than we make it. Maybe we watch because we can, because we have the capacity for curiosity and the tools to satisfy it, because the universe keeps offering moments of beauty and strangeness and we're wired to notice them. Maybe witness is its own justification, needing no deeper purpose than the act itself. 3I/ATLAS won't return. Its orbit will carry it out into the galaxy, where in some distant future it might pass through another stellar system, fall sunward around another star, display its tails to other astronomers if any exist to watch, or it might wander the interstellar medium forever, dark and frozen, an unwitnessed traveler in the immense quiet between the stars. But here, in our solar system, during these autumn months of 2025, it was seen, it was measured, it was understood, at least partially, at least enough to know it was both strange and familiar, both unique and ordinary, both special and representative of countless others like it scattered through the galaxy. That's what we do with our brief window of observation. We gather what we can, we make what sense we can, and we wait for the next visitor to arrive and teach us something new about the cosmos we inhabit. Subscribe now to catch updates when the next interstellar visitor appears in our skies, because there will be another someday, and you'll want to know when to look up. What will you be doing when the next messenger from the stars arrives?